Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry, Paper 2. In the fourth module, we will be studying about alkyl halide reactions. In the first lecture, we will be studying about elimination E2 mechanism. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that will be covered in this particular session include elimination reactions. Basically, we will be studying about E2 mechanism, and in the E2 elimination, we will be studying about what are the characteristics of this particular reaction and the factors that affect the E2 elimination. We will also be studying about isotopic effect and the element effects. Then we will study finally about the Zaitsev rule and the Hoffman rule, which govern the product distribution or regioselectivity of E2 elimination reactions. Elimination reactions of alkyl halides. We are going to study about E2 mechanism. We have so far studied about the nucleophilic substitution reaction. Now we will move on to the next one, which is the elimination reactions of alkyl halides. Let us look at what is elimination reaction. So the elimination reaction is nothing but removal of hydrogen and leaving group from a substrate. Here we are talking about alkyl halides. So elimination of halogen and hydrogen from alkyl halide to form an alkene is called the elimination reaction. So here we had given a typical example of elimination reaction. We have a bromide, secondary bromide. This reacts with KOH. In the presence of ethanol as the solvent, we have to heat this reaction to give the eliminated product, and KBr and water are produced as the side products. So here we talk about dehydrohalogenation, that means removal of hydrogen and the halogen is done. So this is basically 1,2 elimination. In other words, the hydrogen may go from this carbon or from this carbon. That is, if we consider the halogen as the carbon number 1, then adjacent to that is the place from where the hydrogen will be removed, not on the same carbon. So that is why this is called the 1,2 elimination reaction. So here we had given the detailed description. Halogen is on carbon number 1. The second carbon has a hydrogen. The base abstracts the proton followed by the removal of the leaving group to give the alkene. So the base actually abstracts the proton, so it gets converted to Hb, and the leaving group leaves as X minus. The base whatever we can use in this reaction may be a negatively charged one or a neutral one, and this is how the whole process takes place. The base first abstracts the proton, then this bond, the bonded electron is shifted between carbon and carbon, and the halogen takes away its bonding electron. So we end up with the alkene and Hb and X minus. So what is an alpha carbon? Alpha carbon is nothing but the carbon on which the substituent is present. So here the halogen is the one which is present on the carbon. That carbon is called the alpha carbon, and anything adjacent to that is called the beta carbon. So in this case we have the proton on this carbon, and we also have a proton on this carbon. So these two are called beta protons. So this is the basic fundamentals we follow in organic chemistry. As we said, the elimination involves loss of beta hydrogen. That means the neighboring hydrogen is lost. So let us take this particular example. In this case, we have a methyl group here, we have a CH2 group here. So between the methyl group and the CH2 group, if you carefully look at here, this has a 3 hydrogens are there in this carbon. In this carbon, we have 2 hydrogens. So that means this beta 2 carbon has 3 protons and beta 1 carbon has 2 protons. So in the elimination, either one of the proton from here, because these are equivalent protons, so any one of the proton can be removed by the base, or in this case these two protons are equivalent protons, so any one of the proton can be removed by the base. So they do give different type of product. If the proton is removed from this carbon, then we actually end up with a product that is given here. The beta 2 elimination leads to this kind of alkene, and when the beta 1 is removed, we get another kind of alkene. So if you look at here, this carbon, we have a carbon with 2 methyl substituents, the alkene with 2 methyl substituents here, and in this case we have an alkene with an ethyl group. So these two are the two different alkenes which are formed in this particular elimination reaction. This is also called as regioselective elimination. That means between the two isomers, one of the regioisomer is formed in large excess. So that is why this elimination is also called as regioselective elimination. So between the two isomers, one of the isomer is formed in large excess. So let us look at some of the characteristics of elimination reactions. We have a leaving group. This actually takes the electrons along with it. And we have a beta hydrogen, which is basically abstracted by the proton, by the base. So that leaves its electron pair behind. And we have a base which is required for the elimination. So the base will abstract a proton followed by the leaving group. All the three are essential for the elimination reaction. Some of the bases which are used are hydroxide ions, ethoxide ions, tertiary botoxide ions. So these are all the different types of bases which are used in the elimination reaction. And the leaving group is basically a weakly basic anion or a molecule. When we talk about kinetics of the dehydrohalogenation, the rate is directly proportional to the concentration of the alkyl halide and the base. So in the rate determining step, these two concentrations are involved. So that is why this reaction is called E2 mechanism, or the second order kinetics elimination reaction. And if the reaction depends only on the concentration of the alkyl halide, then that is called the E1 mechanism. That is a unimolecular elimination reaction. So let us look at the E2 mechanism. It's a single step mechanism, or it is also called as a concerted reaction. So here the base removes the proton and simultaneously the leaving group leaves. So these two things happen simultaneously. As I mentioned earlier, the leaving group leaves with the substrate with an electron pair. The bonded electron pair is taken away by the leaving group, and the hydrogen donates basically when the hydrogen is subtracted by the base, that leaves the electrons with the substrate. So the result is the olefin which is formed. So when this bond is broken, that is when a base abstracts the hydrogen, basically it is only the proton that is being abstracted. In other words, this becomes H+, that is the bonded electrons are left with this carbon, and this now shifts between these two carbons, and the bond between C and X is taken away by the halogen, that is those bonded electrons are taken away by the leaving group. So that's why here we have the X with minus charge, and both the electrons are there. And this leads to the formation of our alkene. So basically when the base abstracts the proton, the beta carbon gains an electron. The beta carbon shares it with the alpha carbon, which pushes out the leaving group. So once this carbon gains the electron, what it does is it actually shares the electron with the neighboring carbon, and because of that this carbon pushes that leaving group to leave with its lone with its bonded pair. Let us look at what are the evidences for the E2 mechanism. One is it follows the second order kinetics, and there is no rearrangement had seen, because if you look back the SN1 and SN2 mechanism, the SN2 mechanism also does not involve rearrangement, because that is also a concerted single step mechanism. The same way elimination 2 is also a single step concerted mechanism. There is no rearrangement involved. But these show a large hydrogen isotope effect. We will just look at what are these factors. And it is not accompanied by hydrogen exchange reaction. That also is another thing, because which confirms the reaction is a single step mechanism, and it shows large elemental effect. So these are all some of the facts which proves that the reaction proceeds via E2 mechanism. So what is the elemental effect? If an element is changed in the reactant, because we have alkyl halide with Rx, so it can be chlorine, bromine or iodine. So when the halogen is changed, the rate of the reaction will also change. So then we say there is an element effect is observed in that particular reaction. For example, if we with the ethoxide ion, the rate of the reaction of 2-phenylethyl halides are shown here. So the iodide reacts much faster compared to the bromide, compared to chloride, and the fluoride reacts very slow. So because we know the Ci bond is the weakest bond, so the rate of the reaction for this particular reaction will be highest, because the Ci bond is so weak that it can be easily broken. In other words, the reaction is very fast. And we also have something called isotope effect. So what is an isotope effect? That is different entities. Isotope is nothing but the different entities of the same element. So same or similar, they also have the same or similar chemical properties, but they are not having identical chemical properties. So this is the basic definition for an isotope. So in this particular case, the difference in the rate, that is due to larger size. Say for example, if we compare hydrogen and deuterium, deuterium is twice the weight of hydrogen. So there is a large size comparatively, weight is also very high. So it affects the rate of that reaction. And also the position of the equilibrium is also shifted due to the difference in the isotope present in the reaction system. So if these things are observed in a particular reaction, we say there is an isotope effect observed for that particular reaction. So basically what we say is, if a particular atom is less tightly bound in the transition state, this is what is very crucial, of that particular reaction than in the reactant. So we have a starting material, we have a transition state, we have product. We have three different entities. When the starting material is getting converted to the product, it goes via the transition state to the product. So in that case, the reactions involving heavier isotope of that atom will go very slowly. If the carbon hydrogen bond is broken in the transition state, then replacing hydrogen with deuterium will definitely affect the rate of the reaction. So that is what is called isotope effect. So here, as I mentioned, deuterium is twice heavy as hydrogen, and tritium is 3 times heavy as hydrogen. So when we say what is primary isotope effect, we have two things called primary and secondary isotope effect. In the primary isotope effect, the rate change due to isotopic substitution at the site of the bond breaking or bond making in the rate determining step. So in the rate determining step, if at the site the bond broken or bond making involves the isotope, then we say primary isotope. And if it is other than the site of bond making or bond breaking, then we have a secondary isotope effect. That is what we call that. So here the different nucleides are given, CH versus CD, the K light by KD, the rate of light versus rate of heavy at 25 degrees is something between 6 to 8. In the case of CH and CT, it is 15 to 16. So based on that, if there is a difference in the rate between hydrogen and deuterium, then we say there is a primary isotopic effect in that particular reaction if the transition state involves a bond making or bond breaking with respect to the carbon and the other element, whether it is hydrogen or deuterium. Say for example, if we have that CH bond and we have a CD bond, so these two bonds are there. So this is what is called, this is a light isotope, so this is called K light or KH, we can also mention that. So in the transition state, the CHZ are all together in the transition state connected. So if this bond is broken very easily or very difficult, based on that the rate of the reaction obviously are affected. So here the C is produced and HZ leaves out. So here we will get a carbocation basically. And if it is a CD, then we call this deuterium is a heavy element, so we say it is a heavy isotope. And in this particular case, the CD bond will be little bit stronger compared to CH bond. So the breaking of this bond requires little bit higher energy. In other words, the rate of the reaction is slower if we say primary isotope effect observed. So in this particular case, we have KH by KD is observed to be 7. In other words, we say in this particular case, here we have hydrogen, both are there in the first case. And in the deuterium case, we have deuterium here in both the cases. So that means the rate of KH and the rate of KD, when we take the ratio of these two things, the factor is found to be 7. So that clearly tells that the proton compound reacts 7 times faster than the deuterium containing compound. So thus we say this particular reaction involves primary isotope effect. So what is the conclusion? The beta carbon hydrogen bond, that is the carbon hydrogen bond breaking, is the rate determining step. So this is a crucial observation which we can make. So the conclusion is beta carbon hydrogen bond breaking is the rate determining step. This we studied using the isotope effect, primary. And we also saw the elemental effect. So basically, if there is an element effect, then the E1-CB or the carbanion mechanism may not operate. We will study about what is this E1-CB or the carbanion mechanisms later in this session. Right now we will not have to worry about this one, but we will only see what is the elemental effect. So as I mentioned here, for the hydrogen exchange experiment, formation of the carbanion is irreversible. That means in this particular case, what happens is the hydrogen is removed in the first step by the base, which produces the carbanion. So this is what is the intermediate that is formed in the E1-CB mechanism. That is what we say the carbanion mechanism. So if this is the case happening even in the case of E2 mechanism, then our products are going to be different. So we have to study whether this type of mechanism actually occurs in the E2 or not. So if a carbanion is formed, then the carbanion can actually abstract a proton to go back to the starting material, or the carbanion can lose the X minus to give the alkene. So these are all the two different steps possible in this particular reaction. So when we say element effect, then we can easily differentiate whether this type of reaction mechanism is observed or not observed. We can confirm through the elemental effect. So what is the observed fact? When we take RBr, it reacts 25 to 50 times faster than RCl. So that means there is a good elemental effect observed in this particular reaction. So what we can say from that, the RX bond strength is higher than the CH bond. So therefore the rate is also higher compared to the isotope effect. In the isotope effect we had only seen 7. KH by KD was 7, but here in the case of bromine and chlorine replacement, the rate is 25 to 50 times faster. So the element effect is much stronger compared to the primary isotope effect. And here we have an example of E2 mechanism for the elimination. So Ri reacts faster than the Rf if we have to compare the rate for the same alkyl halide. And between the RBr and RCl, generally the RBr reacts 40 to 60 times faster than the chloride. So this is how we say there is an elemental effect observed for this particular E2 reaction. So this we can conclude that rate of the CH bond breaking does affect the overall rate of this reaction. Therefore what we can say, this 1,2 elimination proceeds via E2 mechanism. The primary isotope effect tells that the CH bond is broken in the transition state, and the element effect also shows that the CX bond is broken in the transition state. So that means these two put together proves that the reaction proceeds via E2 mechanism. So let us recap what are all the evidences we have seen so far. The reaction follows the second order kinetics, and there is no rearrangement, and it shows large hydrogen isotope effect. That's what we have seen, 7, and it is not accompanied by hydrogen exchange, and it shows large elemental effect. So these are all the factors which favor, or the evidences which favor the E2 mechanism. And let us look at what is the orientation and reactivity of E2 mechanism. So what is the orientation? Which isomer is the major one? That is what is called orientation. We have something called the sites of role. So in a dehydrohalogenation, the preferred product is alkene that has the greater number of alkyl groups attached to the doubly bonded carbon atoms. So this is what is called the sites of role. So in this particular disubstituted and the monosubstituted ones, we will see the example and then you will understand it. So this is the alkyl halide or the bromide which we are going to take as a substrate. We have a carbon. This in the second carbon has the halide. So this can be lost. So we have a methyl group attached here. We have a CH2 group attached here. So we have a base, hydroxide base is there. So this hydroxide base can first abstract the proton from carbon number 1 or from carbon number 3. So I had put here 1H removal, means the carbon, the proton is removed from the first carbon. So this leads to the formation of 1-butene. Okay, if the proton from the third carbon is removed, that is the 3H removal, then we end up with a 2-butene. So this is the major product. Now you see 1-butene versus 2-butene. So that means this is also called the regioisomers. The regioselectivity is mentioned here. So this is the major product and this is the minor product. So from this what we can say is elimination reaction is a regioselective reaction. And the stability also follows the same trend when we have the tetrasubstituted alkene followed by trisubstituted alkene. Tetrasubstituted alkene means 2R2R2. So total 4 alkyl substituents are there on the carbons. So this is the most stable one compared to monosubstituted alkenes. So this is the trend shown, and E2 elimination also follows the same. So we can rewrite the sites of role that in dehydrohalogenation, the most stable alkene is the fast one that is being formed. So in this particular case, what we can say is if the alkyl group is not present in all alkenes, so the stability of the alkene is rather than the number of alkyl group is the general rule what we say. So in the transition state, what happens is like the base abstracts the proton and the leaving group leaves to give the corresponding alkene. So any factors that stabilize the transition state also stabilizes the product alkene. So in other words, the rate depends on the reaction. Say for example, we have some electron donating groups or electron withdrawing group attached to this carbon. So they also affect the product formation even though they are not alkyl groups. Other groups which are present here may affect the rate of the reaction. So that is what is mentioned here. Now we also have another elimination called Hoffman product. So in the previous case we had seen hydroxide as the base, which is a very small linear base. But when we use a bulky base, then the elimination reaction works in a different way. Instead of the more substituted alkene, we are going to end up with the least substituted alkene. Say for example, we have a tertiary butoxide which is a very bulky base, and this bromine has a proton here on this carbon, a proton here on this carbon, a proton here on this carbon. So the base can abstract a proton from 1, 2 and 3. There are 3 different places. These are identical ones, so we can say there is only one, and here we have another one. So we have literally speaking these two identical as one, this as the second one. So there are 2 possibilities of the base abstracting a proton. So in this particular case, it does not abstract a proton from the internal one, rather it abstracts a proton from the external one. According to this, when we use a very bulky base, the Hoffman product is formed as the major one compared to the sites of one. The sites of one, sometimes people use the spelling for sites of people write it differently, so don't worry about that. This is the most branched isomer. This is the least branched isomer. So Zaitsev rule says most branched isomer will be formed when we use a linear or a smaller base. Hoffman rule says when we use a bulky base, it is going to give the least substituted alkene. So here is a comparison between the same reaction. So in the first case, the proton, this is a linear ethoxide base, which is a smaller one. So this can abstract the internal proton very effectively. So we end up with a 71% of the more branched isomer compared to the less branched isomer. So here it is formed in 29%, here it is formed in 71%. So this is what is called the Zaitsev product. And when we use a bulky base, the less hindered site is where the proton is abstracted. So we end up with this isomer. Terminal alkene is formed in 72% compared to 28% of the internal isomer. And always remember, the reaction is not exclusive like only one product will be formed. If there is more than one possibility of abstracting a proton, all the possibilities may work in many cases. So that is why we get a mixture of product and not exclusively one product. So that is why these particular reactions are called as regioselective reactions. So one of the regioisomer, either this isomer or this isomer, is formed in large excess. So let us look at the reactivity. The stable alkene yields a faster product, that is primary to secondary to tertiary. The more branching is the most favored one, so the faster the reaction will be. So here we have a primary alkyl bromide. Here also we have a primary alkyl bromide. This is ethyl bromide, this is propyl bromide. Here we have the secondary one, here we have the tertiary one. So we have different types of alkyl halides are there. They all give. So in this particular case, we have 3 beta hydrogens. In this case, we have only 2 beta hydrogen. In this case, we have 6 beta hydrogen, and in this case, we have 9 beta hydrogen. So as you know, the primary is the less branched, so obviously in this particular case we have less number of beta hydrogens. So if we compare the relative rate, the primary reacts very slow and the tertiary reacts at a much higher rate. And with respect to the number of beta hydrogens, if you look here also we have a very high number with respect to the number of beta hydrogens. So we can conclude that more beta hydrogens, if they are available for removal, then the product is formed in large amount, and the highly branched one is the most stable olefin, and that is what is found in most of the cases. So the E2 reactivity is like this. We can say tertiary reacts much faster compared to secondary, which reacts faster than primary. So between 1 and 2, between the beta hydrogen removal and the highly branched one, the branching outweighs the number of beta hydrogens. So the stability is the most important one compared to the number of available beta hydrogens. And let us recap what is the E2 elimination we have studied so far. The E2 is a single step mechanism or a concerted mechanism. The reaction rate follows the second order, that is rate is proportional to concentration of the alkyl halide and the base. A strong base is necessary especially for the primary alkyl halides. For the secondary and primary alkyl, they proceed with the E2 in the presence of a base like hydroxides or alkoxides. E2 is stereospecific, we had seen. That means all the participating atoms in the group must lie in the single plane, anti-periplanarity, we call that one. That is, both the leaving group hydrogen and the leaving group should be anti to each other. And this is called the anti-periplanar arrangement, which also makes the double bond formation facile during elimination. We will work out some problems related to this one in the cyclohexyl systems, and then you will understand what is anti-periplanarity. And it follows Seitzef rule. The most substituted alkene is usually the major product. If it follows the Hoffman rule, if it is a, that means it's a bulky base is used, the alkene formed will be the least substituted one. And always E2 elimination competes with SN1, SN2, as both are one-step reactions or concerted reactions. In the summary, we will recap what we have studied in this particular session. We studied about the E2 elimination reaction, basically the E2 mechanism we have studied elaborately. And in the E2 elimination, we studied about the characteristics, mainly the nature of the leaving group and the base, how they affect the reaction. And we also studied about what are all the evidences that favor the E2 mechanism and what is the selectivity in the E2 reactions and the orientation of the products that is formed, what is the reactivity and the factors that govern or affect the E2 mechanism. All these things we have studied in this particular session. We also studied about the isotope effect between hydrogen and deuterium, how much the primary isotope effect affect the E2 mechanism we have studied. We also studied about the elemental effect between the leaving group because in the rate determining step the leaving group, how it affects the reaction, that also we have studied. And we also studied about the Seitzef and Hoffman rule, where depending on the size of the base, how the product distribution varies, that also we have studied. With that, we conclude this particular session.